In this video I'm going to explain the suvat equations. These are equations that allow you to calculate the motion of any object moving with constant acceleration. You can calculate distance, initial velocity, final velocity, etc. And they're called suvat equations because the letters S, U, V, A and T are the symbols representing the 5 quantities that they involve. So let me clarify. Firstly, we'll start with S. S is displacement. And so this is distance in a certain direction from the origin. U, let's do it in blue. U is the symbol for initial velocity. So initial velocity like that. And then let's do green for the next one. V is the final velocity. Okay, so if it starts off at a velocity u and finishes up at a velocity v as it accelerates. Next we'll talk about acceleration. So A is the acceleration. There's purple colour there. And lastly, we'll choose a sort of yellowish colour for T. T is just time. Okay, so S, U, V, A and T are the 5 quantities that are going to be involved in these suvat equations, which will allow you, given certain data, to calculate missing values. Okay, so let's introduce the first suvat. There it is, V equals U plus AT. Let me just explain where that comes from. So it really is just the definition of acceleration. Acceleration is defined as the rate of change of velocity. In other words, it's the change in velocity, that's the final velocity minus the initial velocity over the time taken. Okay, so if we define acceleration as v minus u over t, we can then simply rearrange that, multiply through by t. We get at is v minus u, and then add u to both sides. We get u plus at is v, or if we prefer, v is u plus at. Okay, so the first suvat equation, v equals u plus at, is merely a rearranging of the definition of acceleration. Acceleration being change in velocity over time, so the rate of change of velocity. And we also know that if we had a graph showing speed against time, okay, and it starts off at some value u and ends up at some value v, that this gradient here would be equal to the acceleration. And once again, we can calculate that gradient just by doing v minus u over t in the same manner. So there's our first suvat equation, v equals u plus at. Our next suvat here is S equals u plus v over 2 times t, or u plus v times t over 2. And let me just explain where that comes from. If we think about our graph again, this time I'll draw it with nice red axes. Okay, the speed changes from the initial speed u up to the final speed or velocity v, and t, the time, is how long it takes to do that. Now, S, the displacement, is defined as the area under the graph. So if I just shade in the area under the graph here, that area is equal to the displacement S. So, how do we calculate that area, the size of that area? Well, the easiest way is just to say the displacement is u plus v over 2, which is the average value of the velocity, multiplied by the time. Okay, so we can put that in brackets there, multiply it by the time, which is the same as the equation I've written at the top left. Really, this is the easiest of the suvats to comprehend, because it is just a question of distance being average speed times time, something which you'll hopefully be already familiar with. The third suvat I'm going to introduce here is this one, s equals ut plus a half at squared. Note it's just the t that gets squared, not the a as well. Otherwise I'd have put a squared t squared or something like that, but it's not that. It's half times a, the acceleration, times t squared. Now let's show where this comes from. Once again, let's have some axes. Okay, we're looking at speed against time. And in this case, we're going to do the same kind of thing. So we're changing between u and v, but let's say in this case we don't necessarily know what v is. And just so in a time t. Okay, once again, it's this area that we're interested in finding out. Now, we could quite easily pretend that this is a rectangle at the bottom with area ut and a triangle at the top, and the area of the triangle at the top is going to be a half times the height. Now the height is just v minus u, but we already know that v minus u is at, so we can say half times the height, v minus u, times t, but in this case that will be, because we don't know the final velocity, half at times t, so half at squared, and then we just add them together and it becomes ut, the bottom rectangle, plus the size, the area of the triangle, half at squared. Okay, so that becomes our third suvat equation, s equals ut plus a half at squared. Here is our fourth and final suvat equation, v squared equals u squared plus 2as, and I would suggest the easiest way to think about how this is achieved is just to look at what happens if we combine v equals u plus at with another of the suvats. Let's do it with this one, u plus v over 2 times t, and what we can do is we can combine these to eliminate t, and the way we'll do that is we'll rearrange the first one so that we can show that t is v minus u over a, and then we can put that in to the second one. I'm just going to change colour, so once I've put that t as v minus u over a into that, we get s equals u plus v over 2 times v minus u over a, and if I multiply through by 2a, I get 2as on one side, and u plus v times v minus u is basically the difference of two squares, so I can show that that is v squared minus u squared, and therefore we can rearrange that to say v squared is u squared plus 2as, as required in our initial statement that the fourth suvat is v squared equals u squared plus 2as. So to sum up, here we have the four suvat equations. Firstly, we have v equals u plus at. Next, s equals u plus v times t over 2. Thirdly, s equals ut plus a half at squared. And finally, v squared equals u squared plus 2as. These are the four suvat equations, and in the next video I will explain how they are used to calculate motion of projectiles, particles, whatever it is. You can use these to calculate their speeds and accelerations and so forth.